Hello, this is the 5th video of a 6th complex number series on exponential form for OCR Pure Core Further Mathematics, and it considers summing series using exponential form. In previous videos you have already come across geometric progressions of a form A, AR, AR squared and so on, where A is the first term and R is the ratio. Please don't confuse this with R used as modulus of a complex number. For these geometric progressions, we have formulas for the sum of n terms and the sum to infinity, noting that that ratio must be less than 1. We've already met binomial coefficients NCR and binomial expansions a plus b to the power n. We can also write geometric series for complex numbers, and here we will use z as the ratio being a complex number. The sum for n terms will be a 1 minus z to the n over 1 minus z, as long as z is not equal to 1. Let's consider an example when a happens to be 1. Here we can see that the ratio is simply z. And we could write that as e to the I theta in complex exponential form. Thus s to the n could be worked out as being 1 minus z to the n over 1 minus z, equaling 1 minus e to the I n theta over 1 minus e to the I theta. We could expand this further by using z to the n equals cos n theta plus I sine n theta if we needed to split the answer into real and imaginary parts. This is quite a common technique. For example, using a binomial expansion, c plus is equals 1 plus nc1z plus nc2z squared and so on up to z for power n, where c represents the real part or the cos theta elements and s the imaginary part or the sine theta elements. And this is the binomial expansion of 1 plus z to the n. We can use z equals e to the I theta. Let's look at this further. So 1 plus z would equal 1 plus e to the I theta. If we use a trick in terms of writing the 1 as e to the I theta over 2 times e to the minus I theta over 2, and e to the I theta as being e to the I theta over 2 times itself, using the index laws, then we can rewrite that by taking out the e to the I theta over 2 common factor outside a bracket, where we have e to the I theta over 2 plus e to the minus I theta over 2. And you may remember that that bracket is the same as 2 cos theta over 2. So we can then write it as 2 cos of theta over 2 times e to the I theta over 2. Then 1 plus z to the power n will equal 2 to the n cos to the power n of theta over 2 e to the I n theta over 2. As this is c plus is, and we can also expand that e to the I n theta over 2 into being cos n theta over 2 plus I sine n theta over 2, we can equate the real and imaginary parts. So here's an example. First, we're asked to find the product of those two brackets. If we expand them out, we would get 4 plus 2e to the I theta plus 2e to the minus I theta plus 1. And we can rewrite that as 5 plus 4 cos theta using this formula down here, which we should now be becoming familiar with. I want to choose a geometric progression C plus IS, where the imaginary terms, the S terms, are these. So, looking at this, I need possibly A to be 1, because I can see that each term is multiplied by 1. And if I choose Z equals e to the I theta, that would give me the imaginary part, so that would be Z equals cos theta plus I sine theta. But I need this divide by 2, because there's a factor of 2 there, so I shall divide by 2. And I also notice that I've got alternate signs, so I need to put a negative in there as well. So then I would have that C plus IS equals 1 plus minus e to the I theta over 2 plus minus e to the I theta over 2 squared, and so on. This will be an infinite series, and I can sum to infinity using the A, which is 1, over 1 minus the ratio, so that's 1 minus e to the I theta over 2. If I multiply through by 2 and sort out the negatives, that would give me 2 over 2 plus e to the I theta. I can see that's one of the factors up here. So if I multiply top and bottom by this second factor, I will get 4 plus 2 e to the minus I theta as my numerator, and I can use that result of 5 plus 4 cos theta for the denominator. I can, of course, split that numerator into the real part, 4 plus 2 cos theta, and an imaginary part, the minus 2i sine theta, all over 5 plus 4 cos theta. I also know that that sum to infinity is, of course, this whole geometric series C plus IS. So I can extract the imaginary parts of it to simplify this sum up here. Hence, I am able to say that sine theta over 2 minus sine 2 theta over 4 plus sine 3 theta over 8 and so on as an infinite sum equals 2 sine theta over 5 plus 4 cos theta. So in summary, complex numbers can be used to evaluate certain sums of real quantities more easily than by other methods. So the de Moivre's theorem and the complex number exponential form can be very useful. And it's also worth considering writing integers as multiples of e to the I theta times e to the minus I theta. And most importantly, use the results for cos theta and sine theta with complex numbers in exponential form. This was the last video in the Complex Numbers 6 series on exponential form.